My name is Logan Baer, and I'm a cloud security architect with AWS Professional Services. Today, I am joined by Ryan Tick and Vaishnav Murthy, both cloud security architects with Goldman Sachs. Today, we will be discussing how Goldman Sachs leverages AWS Security Services to automate forensic artifact collection at scale. For our agenda, we will start with the learning objectives for today's talk. We will then explain the problem space and some of the challenges and considerations analysts face when responding to security threats across a large number of accounts. Next, we will dive into how Goldman Sachs solved for these challenges and some of the key benefits of their solution. Finally, we will wrap up with some additional resources to help you create your own security automation solution. Ryan, Vaishnav, and I were recently able to present an AWS Tech Talk focused primarily around how forensic artifacts are collected within member accounts. During that talk, we received feedback asking to provide additional detail on the complete workflow. In the diagram pictured, the forensic capture portion resides primarily in the auto-remediation section to the bottom right. Today, we will focus on the pieces contained in the purple outline. This will include how Goldman Sachs leverages AWS Security Hub to centralize findings and automate security checks across managed accounts, how Goldman Sachs queries additional data sources such as CloudTrail, VPC flow logs, MaxMind, and deployment information, including contextual data to enrich security findings and tune detections, and finally, how these enriched findings are then used to quickly and consistently resolve security incidents by triggering remediation actions, in this case, forensic artifact capture.
Thanks, Logan, for talking about our learning objectives. Before we get into the solution that we developed, we wanted to introduce some of the problems that we faced when we first started to design it. There was a great talk last year by Ross Warren and Brandon Baxter. It's titled Automating Threat Detection and Response in AWS, and we have it linked in Appendix A in our resources slide. But it posed the question, why is threat detection so difficult? We came to a lot of the same conclusions independently, but wanted to give Ross and Brandon a shout out here for their thought leadership in the space. The first point that makes threat detection so difficult is that there are a lot of different data sets. Not only that, but most of these data sets have a unique or non-standard format, which makes ingesting and analyzing more difficult. We'll discuss how we leverage AWS Security Hub to address this problem in the next slide. For the second problem, because of the different configuration requirements between accounts, detections need to be tuned because they have a high rate of false positives. Something that is normal in one account may be abnormal in another account. For example, an intended action taken in a development sandbox account could be an action that should never happen in a production account. Because of that, in our automated solution, detections pull in contextual data and enrich existing information in order to reduce the rate of false positives. Lastly, and the third point which we identified was that there are limited resources. Ross and Brandon spelled out the skill gap in their presentation last year, which was a very valid finding. We wanted to expand that slightly to account for other resources that are limited, such as time and money. As Ross and Brandon discussed in their presentation, it's difficult to find a lot of qualified candidates. Not only that, but these candidates aren't going to work for free, and they're not going to be able to work every hour of the day. With that in mind, we can conclude that it's easier to scale technology and code than it is to scale people. Now that we've identified some challenges, let's talk through how we resolve them. First, in order to account for large varied data sets, we make use of AWS Security Hub in its common data format called ASFF, or AWS Security Hub Finding Format. This allows us to take findings from native AWS data sources, such as GuardDuty, Macie, or Inspector, to name a few, and it also allows us to take third-party data sources, such as your IDS, IPS, or EDR, and we can ingest all their different data findings into Security Hub. In doing so, finding fields are integrated and made consistent. Next, in order to reduce the amount of false positives we have in our detection pipeline, we do a few things. First, we enrich the Security Hub finding so that we can gather more contextual data about the security event. This enrichment includes a lot of valuable information, such as Goldman Cloud deployment and runtime data, contextual CloudTrail and VPC flow log events, as well as geospatial IP address information. With all of these enrichments and insertions, we'll know what happened from both an API level and a network level a few minutes before and a few minutes after the detection took place. We'll also know and can provide context around the purpose of the AWS account within the Goldman environment. And lastly, we'll have some enrichment around any IP address in the finding. For example, maybe a guard duty finding alerted us that an EC2 instance was communicating with a foreign IP address. If we don't operate in that part of the world where that IP address resolved to, this could raise the severity of the security event. And as an added benefit, by allowing for this enrichment, we're able to customize our detections per account and BU. If we need to do any sort of whitelisting or filtering, this enrichment process facilitates that and makes it that much easier to granularly tune our detections. And then with a third point here, in order to combat the limited resources, such as qualified candidates, time, and money, we try to automate as much of this detection and response process as possible. Our solution leverages cloud-native AWS services, which scale with load and are inexpensive. These services also allow us to accomplish different tasks in parallel, as opposed to more serial workloads. So in the grand scheme of things, by investing our time into automated detection and response, we're saving Goldman Sachs both time and money. With automation, we're not looking to get rid of jobs. In fact, we're looking to do quite the opposite. We want to automate away some of the very manual aspects of the legacy process and allow the qualified cyber candidates on our team to focus on different aspects of the response workflow.
We thought the best way to showcase the benefits of our solution would be to establish a storyline and walk through how we would be able to use it to detect, respond to, and remediate a security incident. So for the sake of our story, let's say you get one of these scary high-severity alerts from guard duty, basically saying that one of your EC2 instances, a prod Tomcat server no less, is making connections to a Tor network as a Tor relay. For those in the audience who are not aware, Tor is a framework used for anonymous and oftentimes illicit network communications. So basically this finding is indicating that this EC2 instance has likely been taken over by a malicious threat actor to act as a router or node of this network, and therefore is potentially being used to receive and forward malicious and/or illegal network traffic. So suffice to say, this finding is likely something that you wouldn't be too thrilled to see as an incident responder. Now let's say your weekly AWS inspector scan found that the same EC2 instance did not have SE Linux in the enforcing state, thereby leaving it vulnerable to several privilege escalation attacks. For those of you in the audience who have a traditional incident response background, I can sense the wheels in your head must be turning. This is useful information to know about the potentially compromised EC2 instance, as it points to a vulnerability that may have been exploited by the attacker. An important thing to note here, without foreshadowing too much, is how different these fields are when compared to the guard duty finding. If we had to try and consolidate the findings from both sources into one repository, we might have to invest significant tech debt into an extract, transform, and load workload, which is definitely less than ideal. And this problem becomes exponentially harder the greater the number of event sources get monitored. Now let's explore what should ideally happen next. First, we'd want our SOC analysts to get notified about these findings and be able to access them. Secondly, the analysts would want to start their investigation to answer some important questions. First and foremost being, what is the account used for? Is it a prod account? Is it a dev or testing account? The answer to that question could determine whether this is a hair on fire, all hands on deck emergency, or just an incident that is still serious but confined to a non-production instance, so not as significantly severe. Next, the analyst might want to know the AWS-related scope of the incident. Are there any strange AWS API calls that took place around the time of the event using the instance profile attached to the instance? Also, the analyst might want to find out more details about the anomalous network connections that triggered the guard duty alert. For example, what ports are being used for the connection? Are there any suspicious connections to or from IP addresses?
Now that we set the scene a little bit and introduced our problem statement, we'll discuss Skywatch, which is a solution that we built to detect, enrich, and auto-remediate potential security events. It is also the solution that triggers SkyCollect to collect disk and memory from impacted EC2 instances. We've received tremendous support for our Q3 Tech Talk, but many of you wrote in and asked about our detection process, which allows us to trigger our automated disk and memory evidence collection solution. So Skywatch is our solution at Goldman Sachs that does just that. To start, Let's walk through 3 different detection sources which can fire. On the left here, I have the monitored account, where I want to detect any potential security events. So let's start with a guard duty finding. If a guard duty finding fired in that account, it would be fed into Security Hub. Not only would this standardize the format for me from guard duties format into the AWS Security Hub finding format, but it would also passively replicate the finding into Security Hub in the security account, since AWS makes use of a master member model, where all of the member accounts publish their findings to the master Security Hub instance. So in this case, the member account is publishing this finding passively over the AWS backbone network to the master Security Hub instance located in our security account. From there, we're able to detect this finding being inserted into the master Security Hub instance via the CloudWatch event bridge. And we can use that to trigger our enrichment step function. This will update the Security Hub finding directly via user-defined fields and enrich the finding with some of the data we discussed previously. We're going to deep dive into this enrichment and auto-remediation process in a few slides, but once the finding is enriched, we can leverage CloudWatch events in the event bridge again to determine if we want to trigger auto-remediation actions. If we perform any auto-remediation actions, we update the Security Hub finding to reflect if they succeeded or failed. So that's an example of the end-to-end process for a guard duty finding. But what about CloudTrail? We have custom detections written which analyze CloudTrail data and create findings directly into Security Hub. To talk through that process, we have a CloudWatch log group within our master account that contains all CloudTrail data for that AWS organization. From there, we leverage a subscription filter and send that CloudTrail data to an Amazon Kinesis data stream. In doing so, we are able to read data directly off of that stream. We have a series of detection lambdas set up per service, which allow for custom detections. Once our detection logic triggers a finding, we transform the data and insert it into the master Security Hub instance within our Security Hub account. And then from there, the same process happens as in our first workflow with the guard duty example. We're able to detect this finding being inserted into Security Hub via the CloudWatch event bridge, and we can use that to trigger our enrichment step function. This will update and enrich the Security Hub finding directly. We can then leverage CloudWatch events and the event bridge again to determine if we want to trigger auto-remediation actions. If we perform any auto-remediation actions, we update the Security Hub finding to reflect if they succeeded or failed. And lastly, config is very similar. So if config detects a potential security event, it will generate a CloudWatch event and create a finding in the master Security Hub instance within our security account. From this point on, the enrichment and auto-remediation process is the same as before.
Now that the finding has passed through the workflow that Ryan described in the last slide, it is in Security Hub, formatted in the AWS Security Finding format. The inspector finding from earlier is also in Security Hub in the same format, with its previously disparate fields now all standardized to make it easier for us to parse through. No additional transformation needed. Once the finding is ingested in Security Hub, a CloudWatch event is generated. This is picked up by a corresponding event rule that triggers Skywatch's enrichment and auto-remediation orchestration step function. The step function coordinates updating the finding with enrichment from various sources. So to walk you through some of the enrichments added to the finding, first up we have MaxMind. For those of you unfamiliar with the service, MaxMind is a geo-IP database that we can use to tie down an IP address to a particular latitude and longitude and autonomous system number, or ASN. We can then use this information to categorize an IP address as coming from a potentially sanctioned country, belonging to a VPS provider, or coming from someone's home internet provider, which would help contextualize the API calls coming from that IP address. Next, we have contextualized CloudTrail logs. That would provide the analyst with the API calls that occurred around the time of the incident from the instance profile attached to that Tomcat server, and would therefore help with determining the scope of the event, as it would tell the analyst if the attacker was able to pivot from the instance to affect other AWS services. Then, we have VPC flow logs enrichment, which would help us determine if there were any anomalous network traffic to or from the compromised instance, what port was being used, the size of the packet, and so on. With the enhancements to VPC flow logging in the recent past, we can filter down based on the instance ID instead of the elastic network interface that we had to do in the past. In addition, we're able to enable logging the packet source and destination IP address, so we have better visibility into the original source and intended destination IP address of each packet logged. Finally, we have our deployment database enrichment. This allows us to tie an account to a business unit, determine whether it's a prod, dev, or testing environment, the account owner, and so on. This provides a lot of valuable context to the incident response analyst, along with a clear escalation workflow that can be followed.
The enrichment process described on the previous slide updates the finding in Security Hub and adds user-defined fields. On this slide, we have an example of what these user-defined fields may look like within an enriched Security Hub finding. The first piece of data that we add is from our deployment database. We pull in a lot of registry data, such as the account name, the business unit that the account belongs to, and whether or not the account is a production account. This production flag is very important. We are more willing to auto-remediate findings residing in non-production accounts, since they have a lower chance of causing any direct business impact. As stated previously, we also enrich the finding and provide the location of contextual VPC flow log data and the contextual CloudTrail logs as well. This allows a CERT analyst to quickly use a tool like Amazon Athena or AWS CloudWatch Insights to investigate the detected security event. And lastly, if there's an IP address in the finding, we are leveraging MaxMind to gather geospatial data around the IP address, as Vaishnav described in the previous slide. You can see here this finding has enriched fields that present the city, the country, and the ASN as well.
This is an example of the valuable contextual information we can get from VPC flow logs and CloudTrail. The CloudTrail logs in the orange table shows us that the attackers used the instance profile associated with the compromised instance to perform some standard recon. In this case, trying to list available S3 buckets and EC2 instances. Luckily, the S3 recon appears to have failed, but the EC2 recon succeeded. This was followed by an attempt to launch additional instances, which luckily also failed due to insufficient permissions. Still, this activity shows that it might be worth it to review the IAM policy attached to the instance profile to ensure that the principle of least privilege is being followed. Now from the VPC flow logs in the purple table, we can see the packet source and destination address, which is the original source and destination IP address of the network packet, as well as the instance ID responsible for the connection. So from these logs, we can see that the Tor IP address, in this case 198.51.100.0, is communicating with the Tomcat server 192.168.1.45 on ports 443 and 9001, both ports that are often used for Tor relays. This gives us further evidence that the instance is behaving as a Tor relay. So as you can see, having this information readily available for the incident response analyst to consume can be extremely important to responding to and resolving security incidents faster.
So are we done yet? We've been able to gather a lot of cloud-native data from AWS data sources and enrich that data, but what about traditional host data? And this is where we went into detail in our Q3 Tech Talk. We dived deep on the importance of disk and memory evidence, and we went into detail about the collection process that we developed. If you're interested in this, please go take a look at our Q3 Tech Talk on YouTube. We have it linked in the appendices as well. But if we can level set quickly, disk evidence provides a point-in-time copy and a byte-for-byte copy of all data on any EBS volumes that are attached to the potentially compromised EC2 instance. Disk evidence can potentially help us answer some of the following questions, and we'll frame them around our example guard duty finding of a Tor relay node. The first question, which we may try to answer, could be around root cause. How do we know that an EC2 instance was compromised? Do we see evidence of malware on the EC2 instance? And how did it get there in the first place? We might also want to know how many times has that piece of malware executed? And did the attacker set up some sort of persistent mechanism with the program, allowing it to run on boot or scheduling it to run at a specific time? And lastly, are there any other malicious programs on the instance? Maybe the attacker dropped other malicious binaries onto disk to mask some of their behavior. Moving on to memory now, we would like to capture memory whenever possible and as quickly as we can after getting the alert, since it is volatile in nature. Meaning if I were to restart the EC2 instance without collecting memory, I could lose all of this volatile data stored in memory. And this data is really important in helping us answer some of these following questions. What processes are currently running, and more specifically, what process is the malware running as? What is the parent process of the malware? In other words, what process launched the malware? We're also interested in any network connections that are established. So we're able to see what IP addresses this piece of malware is reaching out to. Maybe it's communicating with a redirector, or maybe we get lucky and can find the IP address of the attacker's C2 directly. And lastly, how sophisticated do we think the attacker is? Do we see any evidence of advanced techniques, such as running the malware only in memory, or using some in-memory encryption technique to mask the malware while it's idle? All of these questions that disk and memory can help us answer are truly invaluable during an investigation. These pieces of evidence will provide insight that we may not see from just AWS Cloud Native evidence sources alone. So this is why they're so important.
So to go over this workflow at a high level, once the GuardDuty alert makes it through the ingestion pipeline and makes it through Security Hub instance in our security account, a CloudWatch event gets generated which kicks off our SkyCollect step function. The step function coordinates cross-account access into the affected account and takes a snapshot of each EBS volume attached to the compromised Tomcat server. Then, the workflow forks, denoted by the dotted line on the left. One fork takes care of the rest of our disk collection process. It creates a copy of each of the snapshots and encrypts them with our shared KMS key, then shares them back with our security account. After this, each of the snapshots is converted to an HDD volume, attached to a custom-built EC2 instance that we call our collector VM, which streams a bit-for-bit capture of the volume to our evidence S3 bucket. The second fork takes care of our memory capture process. Since our prod Tomcat server is in an auto-scaling group, we move forward with collecting memory by executing an SSM document to run our memory collection tool, which in this case is Lime because our server is a Linux server, and also creating a custom memory profile for Volatility, our memory analysis tool of choice. The memory capture, along with the memory profile, is then streamed to the evidence S3 bucket for the IR analyst to process. To recap, one of the main benefits of our approach is that it provides us a near real-time detection and response capability. Ryan will walk you through some concrete metrics that demonstrate this in the next slide. We've also designed it as serverlessly, if that's even a word, as possible. This allows us to scale effortlessly as we're not constrained by the time taken to spin up and down servers, and also allows us to operate in a cost-effective manner as we minimize the infrastructure that is active and idle. Lastly, and perhaps most importantly from an incident response perspective, and doubly important from operating in financial services, is our workflow is completely auditable from front to back, from when a detection is fired to when the disk and memory evidence of an EC2 instance is potentially collected.
In terms of some hard figures, the mean detection to remediation time is about as real time as we could get it. Our legacy solution operated twice a day, meaning it operated every 12 hours. So now we've reduced that time to 70 seconds. And that would mean that the time from when we detect a security event to when we remediate it is about 70 seconds. Next, by aligning to the AWS well-architected framework and really paying attention to the cost pillar, we were able to see significant cost savings and reduce our monthly spend by about 63%. And lastly, the time that it took us to collect EBS volumes fell pretty dramatically. We have an asterisk here because we deep dive into this time savings more in our Q3 Tech Talk. But essentially, the time for us to collect 4 8GB EBS volumes in a manual workflow was about 80 minutes. And that time was reduced to just over 11 minutes via our SkyCollect automated workflow.
Thanks, Ryan. So I'd like to close off by summarizing what we've learned today, and then we will leave you with some additional resources if you're interested in learning more. First, we discussed the challenges of aggregating multiple, disparate data sources across a large number of accounts. We also discussed how security operations centers are often flooded by a large number of alerts and how difficult it can be to filter out the noise from what is actionable. Next, we learned how Goldman Sachs is solving for these problems with the SkyWatch and SkyCollect systems, and the benefits of leveraging Security Hub and the Amazon Security Finding format to deliver events across AWS. We also learned how AWS events can be enriched from additional data sources such as CloudTrail, VPC Flow, and other data sources to add important event context that can be used to influence downstream workflows and automation. Finally, we learned how automating event enrichment as well as remediation can reduce the time an analyst would have to spend on a given incident, resulting in lower costs and faster response times. Listed here is additional content that we feel helps to add depth on incident response and security automation in AWS. The first talk is the talk that Vaishnav, Ryan, and I presented on automated disk forensics. This provides additional information on the workflows that we explained earlier and details step functions, scripts, and expected outputs for both disk and memory forensics. We highly recommend this talk as a follow-on to today's talk. Sec 318 from reInvent 2019 is a great getting started guide for creating runbooks, incident reports, and performing incident response in AWS. And Sec 301 is a fantastic additional resource for security automation. Make sure to also attend or watch Sec 301, 307, and 313 for reInvent 2020. They'll provide very useful information for security responders around working with Detective, Security Hub, Guard Duty, and CloudTrail. As we wrap up, a few things to consider in your implementations. Think about deploying your event aggregation workflow in phases, starting with native services and moving towards third-party integrations and integrations. Security Hub has many native integrations with AWS services, including Guard Duty, Detective, Firewall Manager, Config, Macie, Inspector, and several others. Findings from these services are automatically aggregated in Security Hub Master Account, providing a simple interface to create your security automations. Some third-party services do not yet have integrations with Security Hub. If you are using these products in your environment, you can still use the Security Hub batch import and update findings APIs to ingest important events, leveraging user-defined fields to hold contextual information. This can also be used to create custom alerts from sources such as CloudTrail. As auto-remediation actions are created, consider running as alert only before auto-resolving issues. This will ensure that your remediations are targeting the correct use cases and limit the chances of downtime. Finally, design your workflow to be fault-tolerant. Enable monitoring, establish SLAs, and build in processes to handle errors. And then in Appendix C and D, we've included detailed architecture diagrams for both our CloudTrail and config workflows for you to review offline. If you have any questions, please feel free to reach out to us on LinkedIn, and we'll get you squared away. Thank you for joining, and as mentioned, feel free to reach out to us with any questions.